I want to talk to you a little bit about my background. I want to talk a little bit about what I used to do when I worked in the computer science department here. And then I'll talk about what I'm doing right now. Basically, I build, fly, and often crash drones and other robotic systems. My background's a little weird. When I was in high school, I'm a Nevada native. I went to McQueen, and I really, really wanted to become a lawyer. And so I studied philosophy and math in college. And then I decided to come back here. I was in Seattle up at the University of Washington. And when I came back, I was offered a position in the robotics lab. And they said, we will pay for you to go to grad school, and then we will pay you on top of that. And I said, I love robots. So that's how I got into robotics, completely by accident. It was not my intention. In kind of the same way, I fell into drones. And so basically, I've been getting consistently lucky in my career path for a long time. However, I have liked math for a while. So let's start with robots. So how many of you agree that funding is a big challenge when you're doing robotics? Yes. Yeah, awesome. Okay, so that's actually a really good segue too. I was going to save this till the end, but this is one of the robots that we work with at the university. Does anyone know what this robot or what kind of robot this is? First off, what's the shape of it? Yeah. Humanoid, yes. This is a humanoid robot. Why is it a humanoid robot? Yeah.
Because it's bipedal, it has thumbs.
Yeah, so it has features that we think of as being very human-like. So it's got two legs. Though not all humanoids have two legs, or even one leg. It has two arms, though not all humanoids have two arms, or even one arm. And it has a head. Most of them have heads. So any guesses how much a robot like this costs? So you can hear it. It's got some motors. It's got that Iron Man sound. And it's made of plastic, relatively cheap plastic. So any guesses how much something like this costs? And by the way, the computing power in this is worse than what's in your phones right now. So this is about an $8,000 to $10,000 robot from France. This one's named Sky. It's named Sky because we took it to Roy Gom Elementary School. The first kid that walked in looked at it and she said, "This is Sky." And that was it. We couldn't go with anything else. So in a second, Sky will stand up. But while Sky is booting, because robots are really just computers with some motors, what else is hard? Let's say I give you all the money and all the smart people in the world. What's hard about robotics? Does it just do all the problems go away, or are there still things we need to do? Yeah. Yes, the programming is exceptionally difficult. How many of you have written code before? Cool. How many of you think that writing code is challenging? Everyone who raised their hand. Actually, everyone can raise their hand. Code is challenging. How many of you have to think really, really hard about standing up? Anyone? No? Okay, cool. Keep it that way. So humans do that effortlessly, right? Robots, on the other hand, have to be programmed specifically to be able to stand and to walk and to move around, and that is exceptionally challenging. So much so that that is an unsolved problem in robotics. So you're about to see Sky, hopefully, stand up. I really hope. There we go. Okay, Sky is standing. Sky is not just standing. Sky is actively balancing. If you're over on that side and can't see, feel free to stand up. So that's incredibly challenging. And building a robot that can do that is very hard and will probably continue to be hard for a while. So that's a good one. What else is hard? The thing that you probably most take for granted, the ability to look at people, to understand what they're doing, to be able to talk to them, for them to be able to talk to you, that is, I think, probably the hardest thing about robotics. Even if Sky can stand and can walk around, Sky still doesn't understand when I'm angry because it's not doing what I tell it to do. And until robots can understand that humans are angry, they're not going to be as useful as maybe they could be. Though we kind of have learned some lessons about this. So Sky is doing some interesting things right now. What's Sky doing that's interesting?
Looking at you, I think.
Yes, to both of you. So he said, he being Zachary, said it's swaying. It's balancing. Does it need to sway to balance, though? How many of you think that Sky needs to sway, like I do, to be balanced? How many of you think that's not necessary? Good, it's not. So it's not the physics in this case. And then Lucas said, it's looking at me, right? So if I go over here and I talk, it's entirely possible, and we'll see how good it is, that it will turn eventually to look at me, and it will focus on me. So it's doing those things for the same reason. Why is it doing those things? Why is it swaying, and why is it looking where? Well, why is it looking at me? What? Because I'm the one making noise, right? So it has multiple microphones, and this is actually kind of a cool physics problem. It's got microphones on both sides of its head, and the sound takes different lengths of time to get to those microphones, tiny, tiny, tiny difference. But on the basis of that difference, it can actually figure out the direction the sound is coming from. So it's just like humans, binaural hearing. But why? Why would you program it that way? What do you think would happen if it didn't do those things? If it always just looked straight ahead until you programmed it to move its head, and if it didn't sway? Because swaying is wasteful, right? If I'm swaying, I'm expending energy. I'm putting stress on those servos. I'm doing all kinds of things that mechanically are not good. So there's got to be a reason. So what would happen if you didn't make it sway and move its head and blink its adorable little eyes? Because it's also blinking. So it turns out people find this thing overwhelmingly creepy if you turn off all of the motions. So this is something they learned with the first generation of these robots didn't have that ability to move around. And people hated them. Now they think they're adorable. So I think one of the most interesting things about robotics is that everything we think of as being really hard is actually pretty easy for computers. So how many of you play chess? How many of you have ever played chess? Okay, how many of you have played, do you play Go? Which is like chess, but harder. A couple of you have played Go. So when did computers beat humans at chess? In the 90s, in the last millennium. So that was solved. Computers can beat humans in chess. Now the best computer can handily beat the best human. Go, which is a much more challenging variant of chess, more or less, is still something that the best humans win at. But in fact, this month, one of Google's companies, Google DeepMind, has challenged the best Go player in the world to a Go competition. And it is widely believed that Google's computer will beat the guy. So that's coming up. Watch in the news for that. It's going to be a big deal either way. But those things are things that computers can do. I'll bet that even the Go program on my iPad is probably better than everybody in this room, no matter how good you are. And so with computers, much of what we find very challenging, super easy. But everything that we think of as incredibly simple, next to impossible for robots. So walking, very, very hard for robots. Being able to pick up a bottle of water without crushing it or knocking it over or doing anything terrible. I'm glad the cap was on. Impossible. Very, very challenging for robots to do. Holding a conversation, hard for some humans, hard for all robots. These are things that are exceptionally difficult to get robots to do. And so there's actually a whole field called human-robot interaction that is dedicated to studying the ways that people and computers and robots in particular can interact. So that's what I got my PhD in, was studying how humans and robots can interact. This is a video that we presented to the military because, fun fact about computer science research, the military funds just about all of it in the United States. So what's going on here is a very mundane scene. I would actually say nothing interesting is happening at all, except that we have a computer, or a robot in this case, and what we're seeing in the top two panels is the worldview according to the robot. So on the left, we have normal RGB camera frames. And on the right, the things that don't matter have been segmented away. And it's kind of hard to tell from here, but this is actually the viewpoint of an Xbox 360 Kinect, so the 3D camera. And so those points, you can see how Amol, who was in our lab and now is working for Microsoft in Redmond, Amol looks like he's blotchy. That's because each of those points is actually a point in 3D space. So I can tell you exactly how far away Amol is and how far each of those things are away from the camera. So it sees in 3D, which is exceptionally challenging. And what it's doing down on the bottom, the details aren't really important, though the Navy thought they were, is it's figuring out what Amol is going to do next. So it's looking at the activities he's performing, and it's saying that he's going to clear the table. This is not hard, right? So when she just took a drink from her soda, I knew she was going to set it down and not throw it at me, right? If she had done that, we would have all been surprised, wouldn't we? Yes? Yeah. That is a critical social skill that is fundamental to human-human interaction and is what I spent most of my graduate student years studying. And then one more. So here we have the same sort of setting. Here we have more cameras. You can see that we've got a robot dog. We have a red now. That one was named Marie. This is what the camera sees as being interesting at the time. This is the human in the scene. You can see that it's recognizing objects, which is it used to be incredibly challenging, not so much anymore. And then it's also tracking not just that there's a human, but also where my shoulders are, where my head is, where my hands are, so that it can try to predict my activities. And it's doing it 13 times a second, which is just barely fast enough to be usable. If I turn the sound on, there's ridiculous dialogue. Right now, almost all systems that work in the real world operate through a network connection of some kind. So it's a cloud. They're saying cloud robotics is going to be a big deal. There are some exceptions. Can anyone think of exceptions to that? Tesla, right? So those cars are practically robots. And they're only going to be more and more like robots going forward. And so in that case, almost all of the technology is actually on the vehicle. When we fly drones, some of the bigger drones we fly, almost all of the technology is on the vehicle. But for now, particularly with things like humanoids, that is not really feasible. NASIC, which is the group I'm a part of, is in UNR's College of Engineering, but it is not quite like a standard department. It really is about two things. Autonomous systems is just a fancy word for robots. So we do actually work with robots like that one occasionally. But the other thing we do is we work with companies, trying to figure out how to make money selling robotics technology. And as a result of that, we are primarily focused, that's audio, that's next. We are centered downtown at the Innovation Center in a snazzy building across from the Discovery Museum. And we really focus on trying to find things in robotics that are commercializable, that can make money and bring jobs to the state. Right now, that means drones. So you don't care about that. These are the people we work with, though. So one of the cool things about what I was doing in computer science is that I was able to focus on something very narrow for a long time and learn a lot about everything from the neuroscience of social interaction all the way to how do we get these things to not fall over most of the time. Now, though, with drones, what I do is I really work with people in all kinds of areas to help them figure out how to do cool stuff with interesting technology. So right now, we're working with anthropology to study how we can use drones to help archaeologists map sites across the state of Nevada so that we can put those things online and share them with people. We're working with hydrogeology and geography to study how geothermal power gets generated. So we're flying drones over geothermal plants. We work with engineering and we work with business. But I also get to work with companies too. So how many of you have heard of Flirty? Have any of you heard of Flirty? They're in the news a lot. So they're a drone delivery company. They are based next door in the Applied Research Building. So they're actually based on campus. They performed the first drone delivery in the United States. They did it in Virginia a couple months ago. Drone America is a company that makes some pretty cool stuff. They build things that are much, much bigger. But we also work with groups like NASA, the airport people. So we are actually a part of Nevada's test site. So there are 6 places in the country that can fly drones for testing purposes. So it turns out if you want to fly for fun, you can. And that's totally fine. If you want to fly and you're a company or a university, it turns out it's completely illegal to fly outside. If you do it, then there are $10,000 fines. If you keep doing it, there's prison. It's not good. Not good at all. However, at these test sites, we have something called a certificate of authorization from the federal government that says we can let people fly. And so what we do is we help these people get out. This is actually north of town. And we conduct flight operations, which is actually kind of cool. So I spent a lot of time in offices with things like that. And so now I get to travel all over the country and soon the world flying drones. So it's a neat change of pace. We also teach people. So this was a class we taught. We taught them how to be a visual observer. So any guesses what that means?
You watch?
You visually observe. And actually, you also have to learn some things about how to use a radio. But really, it's all about safety. So we focus on trying to teach people how to operate these things safely. We have a couple of cool projects. So our director is the guy with the remote control there. This is Mongolia. And this whole valley is about to get turned into a lake because they're going to build a dam. There are lots of unfortunate things about this, but one in particular is that there's a type of trout that is actually, I think it's the largest trout in the world. It's huge, the taipan trout, that will probably be destroyed when they dam the river, unfortunately. So what this group was doing was trying to conduct surveys to see how many of them there are, to understand their habitat and the local ecology better. And the way that they used to do it is they'd get biologists to go out in boats, and they'd look until they saw some fish. And then they'd try to catch them and tag them and put them back. As you can imagine, that is challenging and not necessarily super fun. So what they did was they had us come with them and fly. This is one of our drones. Does anyone know what this one's called? It's a pretty common model. It's a DJI Inspire. It's designed for photographers. But our director, Warren, was able to fly over the river and see the fish in a way that biologists had never seen before. And so this, they think, is going to completely revolutionize how they study those rivers. And as soon as there's enough water in the Truckee, we are going to do the same thing here. So we're taking the lessons that we learned in Asia, and we're starting to apply them locally around Pyramid, around Tahoe. So this is one of our current projects. We'll be going back in August. I think I'll be going this time as well. I think by far my favorite stuff to talk about, though, is what we're doing with, does anyone know what this is? I guess let's start with that big thing. Have any of you ever seen this? It's close. It's not here, but it's nearby. So this is in Silicon Valley. This is called Hangar 1. This is an airship hangar. So when the Hindenburg was on the West Coast, it used this. This was one of the largest freestanding structures in the world. It's for blimps. It's at NASA Ames in Silicon Valley. So this is literally right next door to Google. And NASA doesn't just do space. They do a lot with aeronautics, the first A. And one of their big projects right now is trying to build a system for drone traffic management. The goal for a lot of people is to have these drones everywhere, doing all kinds of things. Following cars, though that's kind of creepy, doing search and rescue, performing package delivery, studying agriculture. These are all things that would be very, very cool if we could do them with drones, but you need lots of drones to make them work, right? Yes? In order to make them cheap. So one of the things we're working on with NASA is understanding how to build an air traffic control system for all of these things to coordinate thousands or tens or hundreds of thousands of drones all at once, which is kind of cool. We were actually one of the first groups in the country here at UNR to connect to this system. We drove down to NASA Ames. I took one of my interns, and we hooked up the system that I built to the system they built and checked it out. And then a couple months later, we got to fly with NASA in Central California on an old abandoned military base. And we'll be continuing to do that actually for the next couple of years. This is a very busy slide, but it describes some of the other projects that we are working on as well. So this is probably the biggest one right now. It's called Sense and Avoid. Any guesses what that means?
So they don't crash?
Yeah, so they don't crash into each other, right? So how do you do that? So right now drones have, they have GPS. That is, it's not quite military grade, but it's pretty good. It's surprisingly good. And then they have all kinds of sensors. So you can see they've got radar. And then like you said, they also need cameras. All of those things. So remember how I said everything in robotics that we think of as being really easy is really hard? So getting a robot to see, to recognize you. So I showed the video where it recognized the laptop. Extraordinarily difficult. So now try to imagine that it's seeing and it's going 100 miles an hour, and if it doesn't see correctly, then it crashes. Much more challenging, but also much more fun. So this is a big project we're working on, and then it's actually not on here, but have you flown your drone so far? You couldn't see it? Only when it landed out of your sight. So technically it was out of your line of sight. It turns out right now, flying your drone so far that you can't see it is also illegal. In that case, though, it's fairly sensible because if you're not able to see the drone, you're not able to see what's around it, and you don't know how to take evasive maneuvers if you need to. And so one of the things that we're working on, actually with NASA too, is this problem of getting drones to operate beyond line of sight, which it turns out is rather challenging because of sense and avoid and because of all kinds of other issues. One of the things that people have conjectured is that once we have all of these drones in the sky, they'll be able to sense pressure and wind, and they'll be able to share that information, so we will have a better picture of our environment and our climate and even just the weather than we have ever had before. It already happens in the ocean. Buoys have sensors in them, but we'll be able to do that for the whole planet, which is kind of cool to think about. In fact, one of the things that Ames is working on is trying to build models of how the wind flows in cities. So it turns out, yeah, right, kind of weird, but it turns out that in urban canyons, if you go to a big city with lots of buildings that are close together, wind blows in those urban canyons just because. So if you're outside of the city and it's a perfectly calm day, that doesn't mean it's going to necessarily be perfectly calm in, say, Manhattan. And so understanding the microclimates of those urban canyons is an important problem for just practical business purposes. So I can't tell you who, but I can tell you that there are people working on that right now, which is kind of cool. There are all kinds of things that don't move that you would think would be really easy not to hit. Trees, power lines are kind of another example. Buildings, we really don't want to hit buildings. So how many of you think we could map the world? So we mapped the world once, right? So in the I think it was in the 1800s, we pretty much finished building reasonably accurate maps of the planet, right? Like we knew where all of the coasts were, more or less. And then GIS came along, geographical information systems. We started putting all this stuff in computers, and we did that, and then Google Maps came along, and we were pretty sure we were done then. But how many of you think we could build accurate 3D maps of the whole planet? You're such pessimists. Really? Why? Why not? I mean, we already mapped the planet once, at least once, yeah.
It's always changing slowly.
It's always changing, right? So that's true. So it's going to be hard, exceptionally hard. But once these things fly for a long time, oh my gosh, where's your spirit of adventure? I'm mostly kidding. But I think we actually will have accurate 3D maps of the whole planet. And once we do, it will make a lot of this much, much easier. There are, in fact, companies that are trying to build these databases right now. However, it's a wide open problem. In fact, actually, you're old enough, you probably could start companies and start trying to tackle this right now, which is kind of amazing to think about. The way we're going about it is we're actually turning this space here at, how many of you have been to the air races? A couple of you? Cool. So this is the Reno State Airport where the air races happen. We are turning this building into a research facility where we're going to be studying all of these problems surrounding drones. So if you come back, actually it opens on April 4th. So if you come back in a month, I'll be able to tell you that we are actually conducting research trying to figure out how to solve these problems of detect and avoid and getting drones to operate together. And we'll be doing it for quite some time. So that's what we're up to right now. So this is actually a picture of the air races. So UTM is NASA's system for traffic management. We are turning this whole valley into a research area to study this problem of how you handle air traffic control for drones. We have people from NASA Ames coming up on a regular basis talking about how to do some fairly cool things out here. Drone delivery, I mentioned already. We work with a company called Flirty that is trying to build up the infrastructure to do delivery by drone. And then does anyone know what SAR stands for? Search and rescue. So tomorrow, as it happens, we will be going out, I think, actually to that square. And we're going to send a student volunteer into the middle right before sunset, and we're going to tell them to lie down. And then when we do that, we're going to fly a drone over them, and we're going to try to find them with a normal camera. And then the sun is going to set, and then we're going to use a thermal camera, and we're going to fly over them with a thermal camera, and we're really hoping, and I'm sure after sunset the undergraduate will really be hoping, that we can find them much more easily with our thermal camera than with a normal camera. So the idea is that if someone gets lost up in the mountains, we can find them very, very quickly as long as they're still warm. So that's something that we're going to be working on pretty actively here starting tomorrow evening. This one's not open to the public, though I think future ones will be. Does anyone know what this is? What? It's, yeah, nasty looking. So this is not just a problem with my screen. A couple months ago, so this is Colorado. This is a river. The EPA, the Environmental Protection Agency, screwed up, and they tapped into a mine that was full of toxic sludge. So those 3 humans are having a delightful time in a river of toxic sludge. And so what they've done is they've come to us, and they've said, we want to fly drones, and we want to build very, very accurate maps of this whole region so that we can figure out the best possible way to clean up all the junk. In particular, there are just these big piles of mine tailings, just rocks, that are, maybe they don't have uranium in them, maybe they don't have good enough uranium in them. I really hope they don't have uranium in them because I'm going to be the one flying there. But we're going to be assisting the EPA with that cleanup effort. And we're going to be doing it with a technology called Lidar on one of our drones. So how many of you have heard of Lidar? Anyone? How many of you have heard of radar? Cool. Yeah, so it's just like that, but with lasers. So you shoot lasers out, they bounce back, and then you can measure distances. In fact, that thing, which some of you may have seen walking in, the little puck, is a Lidar unit. In fact, it is the Lidar unit that will be flying over that river. So this can actually build accurate 3D point clouds. In just a second, when we're done with the front, and when my computer decides to uncrash, I'll show you the demo of what it sees. Because we're using it for drones with a big octocopter, but it's also exactly the same type of technology that sits on top of Google's car, the self-driving car. So the same company that makes the lasers for Google is making that laser, which is kind of cool. And it's how we're going to start the project of mapping the whole world. And so these are just pictures of us helping Nevada's economy. This is the drone that we're going to be flying. It's huge. It's like 4 feet across and big enough to carry that kind of Lidar unit. One of the things I like about this technology is that it's really fast moving. So robotics is actually making pretty good progress. There are things we can do now that were impossible 10 years ago. Drones are moving at light speed in comparison. This is a Velodyne VLP-16. It's a Lidar unit, so it's a laser rangefinder, essentially. But there are 16 lasers in here, and it's spinning really, really, really fast. And what it's doing is it's seeing how that light bounces back, and then it's measuring distances. And you can see from those, it's able to rebuild a model of what it sees, essentially. So if I zoom in, zoom out a little bit, you can see me. I'm right there. So watch that blob. It's moving. As you move, I can see you moving. So this is what we're going to be putting on one of our octocopters to build those very, very accurate maps of the American Southwest. This is also the exact same technology that works on Google's self-driving cars. So Velodyne is the company that they actually make a slightly bigger laser that goes on top of Google's cars. And that's how Google's cars are able to see all around them and begin to drive themselves. So what we do is we take this information and we take GPS data and we fuse them together to build very, very accurate 3D maps. We essentially know where we are at all times, and we know how we're moving, so how we're rotating and how we're translating through space. And we take that information, use some clever statistics, and we take these points and we fuse them into very, very accurate maps. I think that we're going to get to a point in the next 100 years where there will be humanoid robots our size that can do everything we can do. Yeah, that will be a thing, I promise. Now, once that happens, we're going to have a whole other range of issues to consider. So drone traffic management is tricky. How are we going to do humanoid traffic management? Humanoid traffic management systems will be a thing in 150 years when we're all dead. Yeah, I think that's right. There will be people who go to school to become robot traffic controllers. Or we'll just have robots do it. I don't know. Because if you think from the perspective of a drone, this is about 600-700 grams, so 1.5 pounds. This is a few dozen grams. The computer is going to be probably 80 to 100 grams. You're talking about probably 2 pounds of stuff. Right now, how long do drones stay in the air?
Not long.
Not long? No? Nothing more specific? Like 5-10 minutes. 10 minutes tops. For the smalls, for bigger ones, 15 to 20 minutes. They can't stay in the air very long, and that's just them by themselves. One of the first things I did when I got a small drone, maybe about this big or so, was I taped an iPhone to the top to just see, well, actually no, to the bottom, to see if I could have just a camera, an iPhone camera on the drone, and it cut the lifetime of the drone in half. So it was interesting. Interestingly enough, I actually think Tesla and actually Panasonic are going to go a long way towards addressing that problem. The batteries that they're developing for these cars are the same sorts of technologies that we will end up using in drones. In some cases, we already do. And so everything that's pushing the electric car revolution forward is also helping us. In fact, one of the faculty here, Kostas Alexis, in computer science, worked with a team in Switzerland, which is where he was a postdoc, to build a solar-powered fixed-wing drone that set the world record for endurance. It flew for 81 and a half hours straight, continuously. So it would charge. It had solar panels on its wings. It would charge during the day. It would draw power at night, and it flew a circular pattern. And they use basically the same batteries that are in a Tesla.